Imogen Fontana, she cannot be here, so I will report.
Can you speak up?
Yes, maybe they can use a microphone. Or maybe there is no need for microphone.
No, the microphone is somewhere there, you know. So you should be.
Can you hear me? No. There is a huge microphone here.
I'm sorry, can I be of service?
Do we have a microphone?
No, actually, this microphone is only for the camera. Huh?
Okay, so
Can you shout?
This is a simple solution. We don't have a microphone.
Yes.
So I will not use it. Okay. My title, my initial title was a bit misleading. This is a big one. Also, EOS on heavy and light millisecond parsers. So this is an explanation. I will be talking about formation of the millisecond parsers, the accretion phase, and the way that we possibly can estimate or learn something from the equation of state. So the main idea is to get such one of those parsers that are young and somehow magically transform them to this region. We know that the parsers are born in this region. There is a region of Krapp and Vila. They have rather high magnetic field and not very fastly rotating, not a very high spin. But this millisecond parsers have estimated low magnetic field and high spin. So I will be talking about this model of spin-up that takes into account magnetic field and magnetic field decay. Magnetic field in the sense of interaction with the accretion disk. And then I will talk a little bit about the interior of the accreting star and apply this accreting toy model, because it's actually kind of a sophisticated toy model, to several interesting, at least in our, from our point of view, interesting parsers, and with some remarks about hyperons in the interior of the neutron star. So this problem is complicated. There are many different pieces of information that one has to take into account, a kind of a synergy of everything. One has to take into account the evolution of a binary. So we begin with the two main sequence stars. One of them is more massive, so it evolves faster. There is a common envelope phase. So then it means that the stars have a chance to be closer to each other due to this. And then it explodes. We have a pulsar, and then this phase is this phase that I will try to explain or describe. A low mass X-ray binary in which the pulsar can be spun up and somehow the magnetic field can be decreased to the values that we observe, or at least infer from the from period and period derivative, because it looks like that we have a currently observed mass of a pulsar, let's say, a measured mass, and period derivative, and we want to kind of link it with the initial values of this pulsar and the amount of accreted mass, the time of accretion. So it's some sort of a population study. So usually that was done in such a way that we assume that we have a Keplerian disk, a thin disk, and simply the matrix accreted from the innermost stable circular orbit, and this equation describes the evolution of the angular momentum. So we have the angular momentum of a particle at the ISCO taken from this orbit and transferred to the star. This works very efficiently, and so with a moderate amount of mass, one can spin up the star to the Keplerian period, that is the mass shedding limit of the rigidly rotating configuration. There is this factor here that describes our lack of knowledge about the dissipation in the zone of unstable orbits, but usually people assume that it's close to 1, and some numerical calculations even show that it's true. So we also can assume that this dissipation in this region below the innermost stable circular orbit is actually low. So the angular momentum is efficiently transferred from the innermost stable circular orbit. The faster the star rotates, the closer the innermost stable circular orbit is. This is a slow rotation equation, but it actually is like that. In case of Kerr black hole, we know that the Kerr black hole is smaller than the Schwarzschild black hole. But so the same works for neutrons. we can also estimate the amount of accreted mass. In case of magnetic field, the things get immediately complicated, and so we wanted to assume something that is on the same level of approximation somehow. So we assume that we have a dipole that is a pulsar that is not pulsating because the angle between rotation and the dipole is 0, the simplest model of the dipole, and in some sort of effective way to estimate the interaction of magnetic field with the disk. So we assume that there are many torque models in the literature, and we took this recent one, estimate the effective radius from which the angular momentum is taken from the disk and transferred to the star. And this is such a, we have to solve such an equation, solve for this, assume that this is 0 because this is then the end of the disk, then the angular momentum is have a minimum, and estimate this R0 that is some sort of an effective radius. So we assume imagined it in such a way that there is some sort of a stable disk, and then there is a region of unstable, destroyed by magnetic field disk, and from this point we take the angular momentum. The additional point is that we assume that the magnetic field decays with the amount of accreted mass. So we have to also assume something like a magnetic field decay, and we assume such a simple law that is partially motivated by observation. It's not perfect, and there are many laws like that. They are more or less all the same, and so we take one of them. And so our evolution of angular momentum of a star now is more complicated. We take this angular momentum of a particle from this effective radius, and there is an addition from this torque model. This time, of course, one can plug in another torque model. So in this sense, it's a kind of a tool that can be used in different settings and then compare it. And as you can see, it's not trivial. It may behave in different ways. When we are in the different places. So this is not necessarily always negative or always positive. So we can have regions in which the star is spinning down or spinning up. Yeah, so this is like that. And just a small digression, we also approximated the whole accretion disk in because to make such an evolution, we have to then integrate the spin up for every time step. So not to calculate all these parameters of the disk exactly, which is we'll be solving every time step solving a space-time around the star, we approximated it with some quasi-Schwarzschild values, and I just showing you. I want to show you that this approximation is actually quite nice, even for fastly rotating stars. So one can have an approximation of a clean accretion disk using some values that are more or less like Schwarzschild values. So we are not really taking into account we don't have to solve precisely the star to get the disk. Although in other words, we can have a tabulated results for the star, and then apply this approximation of the disk to have the evolution of the accreting star. Yes, that was some sort of educated guess, but it works for many equations as well. And I'm also showing you this picture to further prove that it works quite well. This is a mass versus spin, and the difference between the exact position of the this is now without magnetic field. So this is a difference between the exact calculation of a marginally stable orbit and our approximation, and this is below half a kilometer, so it's a few percent difference. So one cannot use it for QPOs, for example, but one can use it to predict the position of the marginally stable orbit, which is good enough for our purpose. So the digression number 2, how the interior of a accreting star looks like. So usually before this work, I thought that accreting stars are very nice because they are accreting matter, so the density inside is growing, so you can expect some crazy phase transitions or exotic matter very fast because it will compress the interior. But we also accrete angular momentum with the accreting matter. And actually, if you look at the accreting star, this simple accretion without a magnetic field, just from the innermost stable circular orbit, this is a frequency versus the central density, and this is this mass shedding limit for the stars of the maximum rotation for a given density. These lines are the spin-up lines, and you can see that they actually, the central density is actually not changing because we efficiently accrete mass, but also we spin up. So it's not so promising for phase transition. And actually, more promising is the spin down because then we really change the density faster with respect to this. But when we take the magnetic field into account, this interaction of magnetic field with the disk, it changes the situation in such a way that then now we have a mass versus density diagram. And again, this mass shedding limit. And these black lines are these old lines to spin up without magnetic field, and the blue ones are with magnetic field. So magnetic field kind of acts like it is kind of making this accretion less efficient in the sense of spin up. So one can recover this optimistic view that the accreting systems are actually nice for phase transition because one can really change the density in the center quite a lot. These points, for example, show you how this magnetic field, estimated magnetic field is changing. So, at least in this model. And yeah. So, what I want to say here also that, in some sense, this inclusion of magnetic field in this picture acts a bit like gravitational waves because it also somehow prevents the star to be spinning very fast. It is, of course, a different point of view because we usually believe that the gravitational waves start to be efficient at some given frequency, and then this is like a wall, and one cannot really spin up because you will expel the energy. And here, in principle, one can spin up to whatever frequency according to some laws of magnetic field decay, but it works in the same direction as gravitational waves. So this is some sort of one should take magnetic field into account while also talking about gravitational waves because it must be important, or maybe important. Okay, so a few interesting stars that we were pondering upon recently. So there are now two very heavy neutron stars. And one of them is the first heavy one, the one that was discovered by Demoras et al. In 2010. It has two solar masses and the frequency of, so it's a millisecond pulsar frequency 300 hertz, so it is interesting from our point of view. And there is another one that is a light one, so the mass is much different, but the frequency is almost the same. So we wanted to see how this accretion process may be different, and also what is minimum mass of the stars. And this picture shows more or less what I already told you about this evolution. So this phase F is the accretion and the spin up, and after that there may other things be important, like the evaporation of the companion and the interaction with the companion that may or may not slow down the star even further. Yeah, so just some information about those systems. There are more or less, well, they are slightly different. The biggest difference maybe is that the current orbital period in case of the massive one is 8 days, and this Black Widow light one is 6 hours. So they evolve in a different way, but which of course is important. So we can produce this kind of pictures. study the amount of time needed to reach the current configuration of a given star with respect to how large the accretion rate must be. So one can plot this. On this plot, every point corresponds to the final configuration of these numbers. So we can plot it for different equation of state. So you can see that there is a slight difference in the equation of state. This DH is the Duchamp-Hansel kind of a nucleonic equation of state, and this one is weak hyperon. So clearly, the influence of equation of state shows up, and it shows up in the thing that is important, this moment of inertia. Because moment of inertia tells us how fast we can spin up the star. And also we produced a plot like that, this kind of spin-up tracks. So these color curves or lines correspond to these values of accretion rate, initial magnetic field, and time of accretion. So this upper numbers are crazy. This accretion time of 7 gigahertz is much too large. So, but this one, it's like 500 megahertz, is more or less all right. So we infer from this that the mass of the star must be more or less around 1.2, maybe a little less, in the beginning of accretion, or in the onset of accretion. So one can play this game and kind of estimate the average parameters, the initial magnetic field, and the initial mass of the star. And the same thing can be done for the massive one. And again, we get the same picture. That the star must be quite massive at the beginning, which may be or may not be a problem for the supernova core collapse simulations or theory of core collapse in general. There are additional assumptions in case of this star. One can put some, from the evolutionary point of view, some time of accretion must be more or less 100 megahertz or lower, and also the interaction at the end of the accretion phase, the so-called Roche-Loeb decoupling phase, means that the magnetic field of the star or the star is interacting with the dilute gas at the end, and it actually makes the star slow down. So it had to rotate faster before to survive through this Roche-Loeb decoupling phase and to get the to be now at this frequency. Do you more or less follow my train of thought? So we had to spin it up faster than it's now, and then the Roche-Loeb decoupling phase slowed it down a bit. But this is a very uncertain scenario, or maybe not uncertain, but the details of this, they are not well known. But maybe one should model that and take it into account. The thing that is interesting in this, that it means that if several pulsars that are slowing very fast, like 700 hertz, they were going through this phase, they were supposed to rotate even faster before to be now observed at this frequency. So maybe they were really rotating much faster than 700, for example. This one it's only 300, but in principle this is a very interesting thing, because maybe the accretion is may spin up the stars to much larger periods than we actually observe them. And this picture shows how it looks like on the mass radius diagram. So this colors corresponds to the previous plots, and you can see that there are. So this is the massive one. This is this massive one. So yeah, one can show this kind of plots to visualize this on this diagram. This is for this hyperonic equation of state. I now have a digression about the estimating of magnetic field, because the magnetic field is usually estimated from the dipole breaking formula, and this is like that. This is actually the lower limit on the magnetic field, and we usually assume that this is 10 to the 45, and this is 10 kilometers, which is not necessarily the case in the case of real neutron stars. And I plot here several equations of state. These dashed lines are equations of state with hyperons, and solid lines are the nucleonic ones. And this number is 1 for the canonical values, so it's like that. It is achieved only, so these are non-rotating stars, for quite massive stars actually. And it's even worse than this, because this value is the maximum for the static stars. When you start to rotate them, this is growing, but this is growing faster, so this actually is even lower for rotating stars, if you take this value as a circumferential radius. So we may make quite a big error on the estimation of magnetic field. And yes, how much time I do have? Okay, very good. So just a picture from Demores et al. That was this famous picture that was ruling out all kinds of extreme equations of state, exotic ones. So we know that below this line, the equations that have a maximum mass that is lower than this one are ruled out. So, and people were cheering because it means progress. Many equations of state were ruled out by this single observation. But during this next couple of years, the situation changed from the point of view of hyperons, changed like that. That theories started to work, and they produced many equations of state that are now compatible with the two solar mass bound. And then it more or less looks like that, that we have such a branch of nucleonic equations of state, and we have another branch of equations of state that are sufficiently stiff to survive the softening by appearance of hyperons. These are relativistic mean field models. And which poses a very interesting situation now, because if we can measure the radius of such a star, especially that the radius is actually constant for this group and for this group in a quite a range of masses, then we can say that if the radius is let's say 12 kilometers, then the hyperons as we want to know them, they cannot exist in neutron stars. Or if we measure 14 kilometers, then there is a hope that there are hyperons in such stars, or that the equation of state may allow for hyperons in such stars. So this is a hope for the future, especially for Loft, because Loft promises the measurement of the radius around 5%. So one probably has to wait for it. So the situation is now it's like that the majority of groups that do the radius measurement, they predict 12 kilometers, but there is a minority that predicts 14 kilometers. And final remark about the spin-up of stars with hyperons or not. The fact that they are bigger, the radius is much bigger than at the same mass than the nucleonic equations of state, means that one spins them much slower. I mean, they are more inertial. So it may be that we don't observe fastly rotating stars because they are big enough not to be spun up efficiently in the time that is available for spin-up. But this is just a hypothesis. So, to conclude, we have created such a sophisticated toy model tool to study accretion phase of millisecond pulses, to take into account the magnetic field interaction with the disk and magnetic field decay, and to take into account the neutron star equation of state, and the evolution of the binary system. So we plug all kinds of information into this and produce the numbers. And in my opinion, the most interesting thing is that one cannot just assume that the initial mass of the star is 1.4 and produce 1.9 neutron star by accretion at this frequency. The star has to be born with such a more or less such a high mass, and one can, in principle, maybe not directly but indirectly study the decay of magnetic field by studying such a evolution. And there are much more other topics of interest, as supernova explosion simulations, that they have to produce such a massive neutron stars, and the initial neutron star mass distribution and spin distribution, And the question what is actually acting in the at the observable population, the magnetic field decay or the gravitational waves, or both. So this is it.
Thank you. So now we have time for several questions. Yes, Michal?
I have one question concerning your picture where you had the radius for the nucleonic and the hyperonic equation of state. I'm not sure if the picture is so clear, because you have, perhaps if you take RMF models, then you have this separation of the hyperonic
Yeah,
ones and
these
the
are just
nucleonic ones.
RMF.
But if you take another model for already for the purely nucleonic ones, you have a much larger spread in the observed radio. So I'm not sure if you measure the radius, you could distinguish between hyperonic and nucleonic ones, because you have so many different models for the nuclear interaction.
Okay. But in the sense when you measure the 14, then you know. If you measure
I'm not
lower,
sure there's no nuclear model which gives a 14
I mean, you may just take the.
I think this is true if you take the relativistic mean field as a model for the nuclear interaction.
Yeah.
But as far as you allow, because you don't know really what is the correct model for the nuclear interaction, so I think
this
can
argument works
kind of
only
be
in
sure.
one way, in such a way that if you the stars that, in our current point of view, the stars that will have hyperons must have a larger radii. So measurement of a large radii implies, I mean, it is not implying an existence of hyperons, but it's not excluding existence of hyperons in this way.
Okay.
So
I see that Leszek has comments.
Yeah.
Okay, so you go first.
Okay, well, I have several comments. One is that high-mass neutron stars were predicted before this observation, about 3 or 4 years ago, both with hyperons. One was in relativistic mean field, Lucky and al., 2006, and the second one was in quark-meson coupling model, which is completely different model. Both of these models had full baryon octet in them, and the predicted masses at 2 solar masses. So it was not that after the observation everybody was trying to fit this observation. It was done before. And I would fully agree with your comment that there are models with hyperons which predict radius around 2.7 or 2.8, which you probably don't know. Sorry, with radius.
Radius.
2 point, sorry,
Mass.
start again. There are models which predict radius about 12.7, 12.8 with hyperons. And this is a very, I would say, subjective selection of equations of state.
Yeah, because just one point to add, because if you take the radius at a 1.4 solar mass, then of course the radius of the star with hyperons depends also on the onset density for the hyperons.
Yes.
And if the onset density is beyond the central density of your 1.4 solar mass star, because the maximum mass star is above 2, then you would see no difference in the radius for the 1.4 solar mass star between the nucleonic and the hyperonic one.
Yes,
what I wanted
it all depends. Sorry, it all depends on which model and which interaction between hyperons and nucleons you take. There are models which would predict, say, cascade spheres, which changes the picture completely because sigmas are away. So I think this is a very simple model, which really I don't believe Loft will give us anything in this context. I am sorry to be very direct, but
No,
if you take
I'm not,
the variety of models you have got, even very precise mass and radius measurement is not enough. Anyway, sorry.
Okay, Leszek, you wanted also comment on that.
This is the problem was, of course, that due to hyperons we have softening, and if we put this softening for star with the radius of 12 kilometers and mass, for example, 1.4, then usually this softening leads to the maximum mass lower than to solar mass. Yes, so if we try to connect this curve where this L is written somewhere there, and so this is the need, of course, that you should have a stiff equation of state below, say, two nuclear matter density to have with hyperons to reach two solar masses. This is just, of course, this is not proof that if you measure 14 and 1.4 solar masses, there are hyperons inside.
Right.
Yeah. Maybe
I think that this discussion maybe we can leave after the
maybe
session. Yes.
Just a brief comment.
Also on the same subject.
I
Yes.
fully support Gina's statement that we are not going to fix this up with love or in the next.
No, but so for example,
No.
let me push it further. So if you observe 10 kilometers, then it will mean that you don't have.
I'm sure that next day you will have 10 papers on Astro PH.
But
But it's not that easy. It's not that easy.
That will
to
happen.
calculate.
Okay, we all know that will happen. You can say it over. Okay, you know that happens all the time. But my comment on my question is, I think that one measure only of one quantity, M over R, wherever, will never be enough precise to really establish a serious question. However, what you have to try to think is, which 2 or 3 correlated measures of different things. For example, we can measure at the same time some other properties like speed period or like velocity or like temperature or age. Then when you try to correlate 3 or 4 observables at the same time with the same model is when you get in trouble. And then it's when things become difficult and it could be really discriminating.
Sure.
But looking only at one,
Yeah, I fully agree. Yeah, sure. That's why you're trying to kind of act in a kind of synergistic way.
Maybe
Okay.
just I have a very short question connected with this figure on which you had the dependence. How it depends when you have different value of magnetic field, how much you can gain for central density. Could you show this view graph? That magnetic field helps you to have higher density. This I don't understand because it seems that if you have higher and higher magnetic field, you are not gaining so much. How
No,
can I understand this? Because you
usually-
don't have the
No,
for
you
the
usually
same
start
model.
with. We always start with 10 to the 12,
Okay.
and then the magnetic field decays.
Okay, so
on
this
the
is
side.
decay and
Yeah.
not okay,
Yeah.
not
Yeah.
the constant magnetic field as it
We
is.
start with this canonical value.
And have you tried to think how situation would change if you have taken into account strange stars? I know that there is a problem with magnetic fields and so on, but have you had any
No, strange
intuition?
stars are
So strange.
radical that we didn't think about.
Okay, so thank you very much, our speaker. The next